Okay, so let's get started, please. So we started to talk about the C programming language. Right, so we saw our first little C program, the Hello World program, in the last lecture. Right, so there's one version of Hello World, right, where we use puts to print a string to the standard output. Remember, puts in a new line at the end automatically. And then we have a return statement at the end. So also remember that the return statement in a C program, that return value gets returned back to the operating system, and that becomes the exit status for your C program. Right, so in Linux, this particular program will exit with a status of 0. Right, now remember, to run this program, you have to compile it first. Right, so we had to do something like this. Right, so GCC hello1.c -o hello1. Right, and that asks the GCC compiler to compile our program, our source code program, and output an executable program hello1. Now I just want to make a quick note about GCC. Right, so GCC is a compiler. So in Linux or Unix, it's just a command. Right, so GCC, some options, some inputs. Right, now modern compilers are incredibly complicated pieces of software. Right, so for example, if you look at the option. So if you look up the documentation for the GCC tool, the documentation is enormous. Right? So here are just the options. So here are the command line options that you can look at. Right? So here are the summaries. I'm going to look at brief list of all options. Right? If you click on that link, here are all your options that go into this compiler. Do I know what all these do? No, I don't know what any of these do. Right? Like I don't know what any of these do, honestly. Very few of them do I actually understand. Right? So these tools are incredibly, it keeps on going. I'm only halfway through the page, right? So a modern compiler, like GCC or LLVM, these are enormously powerful tools, right? You're not even going to, you're just going to learn how to do very basic things with the compiler in this course. But one of the neat things you can do with GCC is that you can stop it at various points in the compilation process. So part of your course notes, there's a notebook called Compiling. And it talks a little bit about how you can use GCC to stop the compiler at various points in the compilation process and look at the various outputs. Right? So step 1 in the compilation process, remember, is this pre-processing step. Right? So if you go back to our program, remember the first thing in our program is this funny statement, right, that begins with a hashtag. Right? So hashtag include. So that's a preprocessor directive. So this is this preprocessor directive. This is the thing that gets read by the preprocessor, right? The first step of the compilation process, and the preprocessor does something, right? So it turns out what the preprocessor does is it takes the contents of standard io.h and drops it into your source code program, right? Now we can ask GCC to run the preprocessor, right? So -E will run the preprocessor for your program. It'll dump the contents to standard out. So I wrote them to this file hello1.i, and then I outputted the contents of hello1.i. Right? So remember what the include directive does. It takes the contents of standard io.h and drops it into your program. Right? So if you scroll past the first few lines where there's a hashtag, there's some stuff here that's used by a later part in the compilation process. Right? So this is the output from the preprocessor. Right, so we scroll past all this, you'll start to see there are these things called type defs. So we'll learn about this in a few days. Right, but this right here, that's the start of standard io.h. Right, so this is the contents of standard io. They got dropped into our program. And you can see that standard io.h goes on and on, right, and on and on and on and on. Right, until we get to, oh no, we're still going. Keep on going, keep on going, keep on going, keep on going, right? Keep on going. Eventually, oh, there's our program, right? And there's the actual contents of our program, right? So that includes standard io.h, causes the contents of standard io.h to be put into our source code, right? And then the next stage of the compilation process consumes the pre-processed output, right? So what it's hard to see because it's hard for you to read because you haven't read C before. But all that's inside standard io.h, it's just the declaration of the functions that are related to input and output. So printing stuff, reading stuff. Right? So basically that's all that's happened. We've just put in the declaration of all these functions to say that, hey, these functions exist, right? So that the compiler can actually compile our little hello world program. Okay, so we can keep on going in the compilation process. So step 2 in the compilation process is this step that's actually called compiling. Right? So in compiling, we take the preprocessor output and you convert that into a lower level programming language called assembly language. Right? So assembly language is basically human readable, is a human readable programming language where the statements in assembly, they closely map to what your CPU can actually understand. Right? So it's something that someone who knows what assembly language looks like can actually read and interpret those as machine instructions. Right? Now, with GCC, you can ask GCC to actually output that assembly. Right? So -s will generate, will write the assembly code that's generated into a file called hello1.s. So if I ask GCC to do that for us, GCC -s hello1.c. Right? Okay, and now if I look at hello1.s, so that's the assembly code for our little program. You can see our little program is not that long, right? And if you look at what's actually generated, right, it looks human readable. Now it doesn't mean anything to you, it doesn't mean anything to me, right? But to somebody who actually understands what assembly language looks like, they could actually read this and interpret this as a program. Now, the only thing I want you to notice here is that there's our call to puts, right? Remember, we're using puts to print something to the standard output, right? So you can see there's an assembly language statement called call, which not surprisingly calls a function, right? It calls the name, so the name of the function is puts, and I'm assuming this @plt has something to do with the inputs to the function. Right? And so that's what assembly language looks like. Now, the vast majority of programmers never touch assembly language after their university education. Right? I'm not even sure in your undergraduate education you'll learn how to program in assembly. But there, occasionally, when you're doing very, very high performance work, an experienced assembly language programmer can very occasionally outperform the compiler in terms of the code that's generated. Right? So in other words, they can write assembly code that's more efficient than the code that a good compiler can generate in very particular circumstances. Right? So in anything super high performance, like a modern video game or anything graphics intensive, there's a high probability that there's a very tiny amount of assembly code somewhere in that program. All right, the next step of our compilation process is this process called assembly. So assembly takes the assembly language program and actually converts that into machine instructions. Right? Those machine instructions are called object code. Right? And like any other part in the process, you can stop the compiler at this point. So GCC -c, hello1.c, will generate the object code for your program. Right? Now I'm not going to do that for you here because you can't actually read this object code. Right? It's all in binary. It's not human readable. Right? Finally, in the last step, there's a step called linking. Right? So it's at the linking stage where all of the various pieces of your program are now assembled into a complete program. Right? So one of the pieces is our object code from our hello1.c program. Right? But there's something that's missing in both the assembly and the object code. Right? There's the call to puts, but if you scroll through the assembly language code, right, you won't see a definition for the function puts. Right? So there's the call, but we don't have the definition. That definition lives somewhere else, right? So it's in another file somewhere on your operating system, right? It's basically in the file that stores the C standard library, right? So the linking stage is where that call to puts gets resolved, right? So in other words, this call, whatever that call to puts is, whatever the code is for puts, that now gets linked into our program to form the complete program, right? So that happens at the link stage. which is the final stage of the assembly language, of the compilation process. Right? So when you do this, right, which is the command I showed you how to compile our program, right? This is actually doing all of the stages at once, right, in sequence. Right? So pre-processing, then compiling, then assembling, then linking. Right? All right. So let's move on to the next set of lecture slides. So that's objects, functions, and types. So those are available to you on OnCue if you want them. So this is basically an introduction to, I guess it's an introduction to types in C. Right? Okay. Now, if you actually read the C standard, you'll quickly come across the term objects, right? Which is unfortunate because in 124 you learn about object-oriented programming. A C object is not the same as an object in a language like Java, right? So in CISC220, the term object means something different than if you're in CISC124, right? So in C, an object is just a chunk of data, just a chunk of memory, right? And inside that chunk of memory, there's some value that's represented, right? So block of memory has a value, right? So that's all they mean by object. So a variable is an example of an object, right? So a variable is some labeled chunk of memory that stores a value, right? Now, fortunately for you guys, variables in C look a lot like variables in Java, right? So they have a type. So int is also a type in C, right? It has a name, right? So in this case, x, right? The naming convention that we use in C is similar to the one we use in Java, right? Although there are no strong conventions in C, unlike Java, where there's a very strong convention for naming, right? So int x declares a variable named x, and it has type int. Now in C, this also causes memory to be allocated for this int value x, right? So when you say int x, you actually get a chunk of memory. That memory can be interpreted as holding an int value, right? So you, excuse me, so you don't end up writing something like new, like you would in Java to make a new object, right? All right. I'm going to show you more types or more basic types as we move along, okay? So functions in C look like a Java method. They also sort of look like a Python function, right? The difference between Java and C is that the main difference is that there are no access modifiers in C, right? So there's no public, private, protected in C. Right? Now, functions are not objects, right? So they're not objects, right? In other words, they're not a label, they're not a chunk of memory that stores a value. However, they do have a type in C, right? So functions are in fact types. I'm going to tell you what that type is later on, right? So for now, just remember functions do actually have types. Okay, and this is the part that's new. It's going to be new to most of you, right? C has this thing called a pointer, right? So a pointer is a variable that stores a link to another object, right? So right away, it kind of sounds like a reference from Java or Python, right? And it sort of is a reference, as in Java and Python, right? So in C, that link is specifically the memory address of an object. Right? So in other words, a pointer stores the memory address of an object. Now that's similar to what a reference is, or what I told you, or what me or somebody else would have told you a reference is in Java, right? But unlike references, you can do a lot more with a pointer in C than you can do with a reference in Java. Right? Okay, so remember, pointer stores the address of an object. All right, so how do you make a pointer in C? Right? So the syntax is a bit odd, and it's inconsistent. All right, so the type of a pointer is derived from the type of the object that you're pointing at, right? So if I have an int somewhere, I can make a pointer to that int, right? So if the type of the object pointed to is t, then the type of the pointer is pointer to t, right? So if I have an int, then the type of a pointer to that int is pointer to int, right? How do I declare a variable that's a pointer? You write the name of the type that you want to point at, right? So I'm going to write int, and then you add a star, right, or an asterisk, right? Now it turns out in C you can write it in 3 different ways, right? So you can write int no space star, int space star something, or int space star space something, right? So in all three examples, right, these all declare a variable called p, right? So there's a variable called p, and all three examples, p points to an int, right? P is a pointer to an int object, right? So the first form is common in C++. The second form is what is used to program the Linux operating system, right? The second form is the one I'm going to use throughout the course. The third form is legal but less commonly used, right? So the compiler doesn't care which version you use. I would recommend you use the second version in this course, or when you program in C in general. But like I say down here, there's no agreement on to which of the above you should use, right? So there is no preferred syntax. They all work, right? So again, one more time, p is a variable, right? Its type is a pointer to int. Okay, so when you call a function in C, it's exactly the same as calling a function in Java. Both languages use pass by value, right? So the arguments that you pass to the function, they are passed by value, right? So in other words, you take the value of the argument, you make a copy of it, and that's what the function gets, right? When the function returns a value back to the caller, right, you make a copy of that value and pass the copy back to the caller as the return value, right? And this is exactly what happens in Java, right? So here's your little Java program that doesn't work the way you want it to, right? So I've got a method called swap, right? Takes in two ints, x and y, and presumably what it does is it switches the values of x and y, right? So down here, if I call swap with 1 and 2, right, then the naive assumption is that when I print out x and y down here, x and y will be 2 and 1, right? Their values will be swapped, right? This doesn't work in Java, which you should know, right? Doesn't work in C either, right? So here's the exact same program in C, right? So we got a function swap. It has no return value, so it's void. So I've got a function swap, no return value, so it's void. It takes in an int and an int, right? Notice the code's exactly the same, right? Is line for line the same up into the print statement, right? The main function, of course, looks a little bit different than the Java main method, right? But everything's the same. Okay, so the way this works is, right? So when I call the swap function here, I take the value of x, right? That value is 1, right? That value 1 gets copied into this x up here, right? Then we take the value 2, or y, which is 2, so that 2 gets copied up to here, right? Now, temp gets the value of x, so temp gets the value 1. X gets the value of y, so x becomes 2, right? Y gets the value of temp, so y becomes 1. So inside swap, that x and that y have changed values, right? It's now 2 and 1. But that x and that y, that's not the same as that x and that y, right? The reason this method doesn't work, or the reason this function doesn't work, is because it switches the values, but it does not switch the actual objects. That's what I want to do, right? I want to store the value, right, that's stored in the object x, right? And I want to switch that with the value that's stored in the object y. The problem is the function does not know about the objects x and y, right? All it knows is it gets the value 1 and 2, right? So this doesn't work. Now, how could I make swap know about the objects x and y? Well, if I told swap what the address of x was, and if I told swap what the address of y was, well, then I could switch them, right? Because I can go and look at the address where x lives, I can get its value, right? Then I can go and look at the address of where y lives, and I can get its value, and then I can switch their values, and everything would switch, right? And that's exactly what pointers are for, right? So swapping two values owned by the caller doesn't work because the function never gets the variables that store the values, right? But if I use pointers, I can in fact get those objects that are storing the values. So I can rewrite swap like so. Okay, let me just quickly go. Okay, so I'm going to explain this all one line at a time, right? So instead of taking in an int x and an int y, I'm going to take in a pointer to an int, and I'm going to take in a pointer to a y, right? I'm going to take in 2 pointers to ints, right? So I'm going to pass in the address of an object for x, and I'm going to pass in the address of an object for y. Now, I want to get the value that's stored in this object that's pointed at by x. Right? So there's a funny syntax for doing that, and I'm going to describe that on the next slide. Right? So I'm actually going to swap those values here to call the function. Right? I can't pass in x and y, right? Because x and y, those are just two ints. Right? I need to pass in a pointer to x, and I need to pass in a pointer to an int, and I need to pass in a pointer to an int. Right? So I need the address of x, and I need the address of y, and that's what the ampersand is for in C. All right, so let's take this apart one line at a time. So there's our swap function. Right? Instead of taking in two ints, I take in two pointers to int. Right? So if x is a pointer, and it is, right? X in this case is a pointer, right? Then star x is the object that x points to. Right? So if x is the pointer, then star x is the object that x points to. Right? So we call that a pointer dereference. Right? So when you write star x, where x is a pointer, right, you're getting the actual object that x points to. So we say that you dereference the pointer to get the object that x is pointing at. Right? So remember that. So star pointer name means you're dereferencing the pointer to get the object that's pointed at. Right? So star x gives me the object, right, that's actually pointed at, the int object that's actually pointed at by x. Right? That's just an int value, so I can store that in an int variable. Right? So if x is a pointer, star x is an int. Right? Okay, now x is a pointer, right? Star x, that's the object that actually stores the value that in x. Right? Star y, that's the object that actually stores the value in y. Right? So star x equals star y takes whatever is stored in the object pointed at by y and stores that in x. Right? So whatever int is pointed at by y now gets stored in the object that was pointed at by x. Right? So in other words, I actually put, when this line here actually takes whatever value is stored, so it takes the value 2, right, and is actually going to store that in that variable x here. So it's going to write a 2 here. Right? Now star y, that's the object pointed at by y. Right? I'm going to store the value of temp in that value. Right? So in this example here, when you call it with 1 and 2, it's going to switch the 2 and the 1. Right? And that works because we have pointers to those two variables, x and y. Right? So on that second line, the object pointed to by x is assigned the value of the object pointed to by y. Right? And then the object pointed to by y is assigned the value of temp. Right? Okay, to call the function, I need the addresses, right? I need two pointers, right? So I need the address of x and I need the address of y. Right? So if x is an object, then ampersand x is the address of x. Right? So the ampersand in this context is the address of operator. Right? And this actually works if you run the program. Right? So here is, so this is swap. So that's the original version of swap that takes in an int and an int. Right? This one's slightly different. It actually prints out the values when you're inside the function and when you're after the function. So if I run that, right, I'm going to try to swap 1 and 2 in x and y. Right? So inside swap, right, x and y, they actually switch to a 2 and 1. Right? But after calling swap, x and y is still 1 and 2. Right? It's this x and y that got swapped and not that x and y that got swapped. Right? There's the one that uses a pointer. Right? So if you run that, right, inside the swap function, x and y have really swapped. Right? So when I print out the value of x, percent definite, right? So when I print out the value of the object pointed at by x, right, and I print out the value of the object pointed at by y, they really are 2 and 1. Right? And after swap is called, right, x and y really have swapped values. Right? So if you want to swap values, if you want to swap two values using a function in C, you have to write the function so that it takes in a pair of pointers. Right? Similarly, in Java, if you want to swap two values, you can't do it if they're primitive types, right? Because there's no way to get the address of a primitive type in Java. Right? Now, if you pass in two objects to a function to a method in Java, it's possible that you can swap the state of the two objects, right? But you'd have to call methods on the two objects to do the swapping. All right, any questions on pointers? We're going to see a lot more pointers later on in the course. Right now, this is just the quick and dirty introduction to them. Right? Any questions? So remember, a pointer stores the address of an object. Right? If p is a pointer, star p gives you back the actual object. Right? If a v is a variable, then ampersand v gives you the address of the variable. Right? Yes?
Why do we have to put the dereference operator in the parameter of a swap?
No, those aren't, no, that's not the dereference operator right there. Right? That's not dereference. So this is declaring a variable, right, whose type is a pointer.
Oh, okay.
Right? Yeah, so that's not a dereference there.
Okay.
Right? All right. So like any other programming language, C has this notion of scope. Right? So scope is just the part of your program where the name is usable. Right? So you know about scope from Java and Python, right? So if you have a parameter in a Python function or in a Java method, the scope of the parameter is the body of the function or method. Right? C has different types of scope, though, compared to the other two languages. Right? So C's got something called file scope. It's got something called block scope, something called function prototype scope, and something called function scope. We don't care about 4 in this course. Right? But the first two are important. The third one comes up only rarely in this course. Okay, so let's look at file scope. So file scope is the closest thing to what you would know of as a global variable in Python. So if you create an identifier, so a name, right, and you declare it outside of a function or outside of a parameter list, right, then that identifier has what's called file scope. Right? So what does that mean? It means that identifier or that name is usable everywhere in the file that it's declared, starting at the point where you declared it. Right? So, for example, here's our C. This is a single C program, right? One C file. Right? At the very top, I have a variable that's declared, right? So I have an identifier, J, right? I have an identifier, J. So the name J is usable in this program from this point onwards, right? So everywhere in this program, that name J is usable, right? And refers to an int in this case, right? So this has what's called file scope, right? That name J is usable everywhere. If int J was declared here, right, then the name J would be usable from this point onwards, right? Now, everywhere you see an arrow, that's where I'm actually using that variable J, right? So here, when I print out the value of J using printf, right, it's the value of that J there, right? Again, when I use that J here, it's that J up there, right? So the arrows tell you which J I'm referring to at this point. Now notice here, there's another J, and here there's another J, right? Those two J's don't have file scope. Okay, so you know about braces from Java, right? So braces denote what are called blocks of code, right? Just like they do in Java. If you declare a variable inside of a block, right, or inside of a parameter list, then that identifier has what's called block scope, right? So in other words, the identifier is usable anywhere inside that block. Right? So here's a function called f, right? Notice there's a brace here, right? There's a brace here, and there's a parameter I, right? So that parameter I has block scope. It's usable anywhere inside this set of braces, right? So where am I using that I inside this function? Well, right here. Right? So when I do I++, when I print out the value of I on the next line, right? And then when I print out the value of I on the last line. Notice here, there's a loop that also declares a variable I, right? That I is not the same as that I, right? So it's not the same. So scopes can be nested, right? So in other words, you can put a block inside of a block, just like you can do in Java, right? Identifiers with the same name, can be declared inside of different scopes. Right? If you declare an identifier at an inner scope that has the same name as an identifier declared at an outer scope, then the inner name takes precedence, right? And the outer scope name is hidden. Right? So here's J, right? Notice there's a J at file scope. There's also a J at local scope, at block scope. Right? Inside this function f, that J takes precedence. There's no way to get to that J inside of this function f now. There's no way that I know of anyway. Right? So now this J is going to hide the file scope J. Right? So when this J is used there, and it's going to be used there. Right? But notice there's another J. Whoops, sorry. There's another I here, and there's another J here. Right? So that I hides the parameter I. Right? So inside this loop, it's that I that's being changed, right? And not the parameter I. Right? Inside the loop body, there's another J. Right? So inside the loop body, whenever you use J, it's that J that's being used, and not that one, and not that one. Right? So that J hides that J and that J inside the loop body. Right? So when you write J here, or when you use J here, it's that J that's being used. Okay, and now if you actually type that program in and run it, you'll see that it prints out a bunch of values. Right? And if you trace through the program, you can see, hopefully you'll be able to figure out which I and J is being used at which point in time. Right? But the arrows tell you on all the slides which I's and J's are being used at any point in time. Right? Okay. Finally, there's something called function prototype scope. So in C, there's something called a function prototype. So that's when you write down the return type, the name, and the parameter list for a function, but you don't give it a body. Right? So you write down the name, return type, name, parameter list, no implementation. Right? That's called a function prototype. So that's telling the compiler that there's some function that returns some value with this name and these parameters, but I haven't told you what the implementation is yet. Right? You're just saying that this function exists. Right? Okay, so you can compile a C program, right, where you've got a function prototype, but you don't have the function definition. Right? So you can compile a program where you only have the prototype and you don't have the actual definition. Right? The reason you can do that is because the compilation process doesn't care until you do the link. Right? So at the point where you have to link your program into a runnable program, that's where you have to resolve where is the definition of this function. Right? But to actually compile the program, you don't need the definition. Right? Okay. So a parameter in a function prototype has function prototype scope. Right? So here I've got a function declaration. Right? So returns nothing. Its name is some function. It has one parameter whose type is int. Right? Semicolon. So there's no function body. Right? So in other words, I haven't defined some function. Right? But I have declared that it exists. Okay? Right there is your parameter. Right? So that parameter A has function prototype scope. Right? If there was a definition, it would have function prototype scope and block scope. Right? Because it would be usable inside the block of the function body. Okay. Now why does this matter? Because you can declare a function like this. Right? So returns nothing. Its name is another function, right? Its first parameter is an int n. Its second parameter is an array of int, where there are supposed to be n elements in the array, right? So here, the fact that n, right, is declared before the before the array is declared is important, right? If you switch these two around, right, you get int a square bracket n. Right? The compiler will complain it doesn't know what n is. Right? But because n is declared first, you can use it later in another variable in the parameter list. Right? So that's the only time that function prototype scope matters in this course. Right? So it's when you're using a variable and you want to specify something about the size of the array, right? Because that's what this is doing. This is saying that you have an array of int where there are at least n elements in the array. Right? That's what you're trying to say in this right here. Okay. Just as a brief look ahead in the rest of the course, this doesn't actually work, and you'll see why as when we talk about arrays and pointers later. Okay. Any questions so far? All right. So we know about variable scoping. We know about objects. We know a little bit about pointers, but I don't expect you to be able to use them effectively yet. Right? Now you need to know about how long does an object exist in C. Right? So remember in Java, the programmer is responsible for the lifetime. Well, the programmer is responsible for creating the object. Right? So when you make a reference type variable, you have to normally you make an object using new. Right? So in Java, the programmer is responsible for the birth of the object and the allocation of the memory. Well, they're not responsible for the allocation. They have to call new to get memory for the object. Right? But you don't care about when the object dies. Right? In other words, you use the object and then you don't actually explicitly have to get rid of the object. That's not the case in C. Right? So in C, you actually control when is an object created, right? And you can control when it goes away in some circumstances. Right? So in C, there are 4 kinds of what are called storage duration. Storage duration is the lifetime of an object. Right? So there's something called automatic storage duration, something called static, allocated, which is going to be the important one later in the course. And there's something called thread storage duration, but that doesn't make sense until you do your operating systems course. Right? So we're not going to talk about that one. Okay, automatic storage duration. So when you have a variable that has block or function scope, right, or block scope, right? So in other words, a local variable, right, or a parameter, that thing has automatic storage duration. Right? So storage is allocated when the block in which the object was declared is entered. Right? So in other words, if you have a function that's got a parameter a, right, then when you call that function, that's when storage for that variable a that's when that variable a becomes alive. Right? So storage is allocated for a, and then it's usable. Right? So here, right, I has block scope. Right? It's usable inside the function f. Right? So as soon as someone calls f, right, that's when space gets allocated for that variable I. Right? So someone calls f, some amount of memory gets allocated for an int I. Right? Whatever argument is passed to the function gets stored in I. Right? So what is the lifetime of I? Well, the lifetime of I is the lifetime of the function. So when that printf statement finishes running, I goes away. It's no longer usable. Right? If you try to use I somehow, right, it won't work. Right? Or, sorry, in C it may work, but it's not guaranteed to work, and that's the really annoying part in C. Right? Now you might ask, so look, I is only defined inside this function here. How could I possibly use I outside of this function? Right? And the answer is, right, if you take a pointer to I and return that pointer back to somebody, so if I change the return type to int star, right, I can pass a pointer, I can return a pointer to that variable I. Right? So whoever calls the function gets a pointer to I. If they try to use that pointer to get to the object, bad things will probably happen. Why? Because I only exists for the lifetime of that function. Right? If you return a pointer to that variable and try to dereference that variable, almost certainly something bad will happen. Right? Notice I'm being very vague about something bad will happen. Right? In C, you have no idea what's going to happen if you end up accessing an object that's no longer alive. Right? If you're lucky, your program crashes. If you're really unlucky, your program runs and it runs correctly. Right? And then somewhere in between, sometimes it runs correctly and sometimes it doesn't, and there's no way for you to know what's happening. Right? So in C, you have to be very careful about exactly what it is you write. Right? And that's why I'm spending all this time belaboring these points. Right? C basically takes off the training wheels that you have in C, Python and Java. Right? You can do a lot of unsafe things in C. Okay, here's another example, right? So I, right? Again, I has block scope, right? It's usable inside this for loop, right? Similarly with j, right? So when you enter this for loop, that's when storage for I gets allocated. When you exit that for loop, that I is no longer usable, right? So that's automatic storage duration, right? Basically, any local variable has automatic storage duration. Okay, static storage duration. Remember, we had that file scope variable j, right? That file scope variable j has static storage duration, right? So anything declared at file scope has static storage duration, right? It's also the storage duration of block scope variables that are declared static. Now I'm going to tell you about that in a second. So the other confusing thing between learning Java and C is that the word static means two different things in the languages, right? So static in C means something completely different than static in Java, right? Okay, so if something has static storage duration, its lifetime is the entire lifetime of the program, right? The variable or variables, right, that have static storage duration, their values get set before your main your main function runs, right? So every C program starts at a main function, but before that main function runs, anything that has static storage duration, its value gets set first. So J has static storage duration. Oh, these variables, haha, I lied to you, these arrows are wrong. Okay, so that J has static storage duration, so it becomes alive and usable just before you call the main method, the main function, right? And its value gets set to something. Okay, so there's also static local variables or static block scope variables. Right? So here, I've got a variable that's an int, right? Its name is counter, right? I set its initial value to 0. Okay, notice that it's marked static, right? So by marking it static, this thing automatically has static storage duration. So its lifetime is the duration of the program, right? The value of counter gets set to 0 before the main function runs, right? So before you run the program, counter gets set to 0. The value of counter is maintained by the function between calls to the function, right? So in other words, when I call increment the first time, right, coming into the function, the value of counter is 0, right? Counter plus plus changes the value of counter to 1, right? And then I return the value of counter, right? So the first time I call increment in this loop, it's going to print out counter equals 1, right? That value of 1 stays or is maintained between calls to the function, right? Because it has static storage duration, right? So the next time you call the function, counter is now 1, right? So in other words, this counter equals 0, this line does not happen every time the function runs, right? It gets initialized once, right? And only once, right? This line runs every time, right? So when counter is 1, counter plus plus makes it 2, right? So the second time this loop runs, it says counter is equal to 2. You run it the third time, counter becomes 3, and then 4, and then 5, and then 6, and then so on and so on and so on, right? So this is C's way of maintaining state between function calls, right? So instead of using an object, right, you can use a static variable, and the value of that variable will be maintained between calls to the function. I don't think we actually making you use this for anything in this course. It's not super useful, to be honest, but it's a feature that you need to know about. Okay, so how do you initialize these things? So static variables are normally initialized when you declare them, like that, right? If you don't initialize it when you declare them, then C initializes it for you, right? So if you have a pointer, right, so if you have a static local variable and it's a pointer, then that pointer gets initialized to null, right? The null pointer, which is a pointer to nothing, right? So it points to no object. If it's an arithmetic type, so if it's a numeric type, it gets set to 0. Now, if it's an aggregate type, which I'm going to tell you about a little bit later, then every member of the aggregate type gets set according to those rules, right? And furthermore, if it's a union, it's the same thing. Well, it's almost the same thing. But we may talk about unions later in the course. Right? These aggregate types are called structs, and we will definitely talk about those later in the course. Right? Oh, okay. That would be a good place to stop. Right? Okay, so there was actually quite a bit of material there that you should review and make sure you understand, because it does impact everything that happens later in the course. All right, so I will see you Wednesday.